Dawn, February 15th, 2011, Boulder, Colorado. The team at the National Space Weather Prediction Center begins its day as it usually does, carefully watching the surface of the sun.
Okay, a 10 centimeter came in today.
Although 93 million miles away, forces here can impact Earth in surprising and destructive ways.
For the smaller,
The M6.
for the M6, you see this. The very first one is the M6.
Today, after years of relative calm, a satellite detects something. A dramatic explosion on the sun's surface. A violent solar storm that would dwarf Earth is erupting, releasing a massive shockwave, hurtling towards us at over 1 million miles an hour. Right now, no one is sure what to expect.
But I think that the M6 is going to get here.
We have to determine when that thing is going to impact Earth's magnetic field.
8 hours.
It's going to be sometime tomorrow, perhaps later in the morning, later at night. That's exactly what we're trying to determine. In fact, I have to join the discussions right now, so I'll get back with you.
The team models the approaching storm.
So 15Z for the arrival of the CME. This
Right,
is it here.
right
okay.
there.
Their simulation shows it racing out from the sun on the left towards the small dot on the right,
So we're looking at about
Earth. The solar storm carries a 1-2 punch. First is a solar flare, releasing an outburst of X-rays that can reach Earth within minutes. The second, more ominous threat arrives a few days later, a phenomenon called a coronal mass ejection, or CME. It's a wave of billions of tons of electrically charged particles, seen here in this repeating image as it ripples away from the eye of the storm. Together, they could hit like a cosmic tsunami. Delivering a surge of radiation and an electrical spike of trillions of watts, potentially crashing the power grid. Sound far-fetched? In March 1989, in Quebec, Canada, that's exactly what happens. One by one, power stations crash, disabled by the overwhelming power surge caused by a CME wave. In less than 2 minutes, 6 million people are left without power. Recently, NASA's Jim Green finds evidence that an even bigger solar storm hit Earth in 1859.
And what we found was the granddaddy of geomagnetic storms, and that was just 150 years ago.
The reports tell of auroras, brilliant displays in the sky. They're so bright that miners in Colorado wake up and go to work thinking it is dawn. Other reports tell of a more harmful impact on the lone electrical system of the day, the telegraph.
One, for instance, because of the induced current on their system, overheated the battery and started a fire, nearly burnt down the telegraph office. Another operator was burnt so badly he ended up into the hospital.
Green uncovers numerous reports of auroras seen not only across the United States, but around the world. The evidence is clear. Earth was struck by a superstorm in 1859, the result of 2 massive CME waves.
Those 2 storms were not only enormous, but they happened one right after the other. No one alive has seen anything like it
If we had a geomagnetic storm of that intensity today, the National Academy suggested that the impact on critical infrastructure could be catastrophic. And the big concern is the electric power grid.
The massive electrical surge from a CME wave could overload power lines and melt transformers, blacking out entire cities.
Repair could take weeks, months, and even in a worst-case scenario, the National Academy suggested up to 10 years for a full recovery.
If that occurred, if you can imagine a world without electricity, you're really going back in time.
It's not just the power grid that's at risk.
More and more, we rely on technology that could be affected by the sun. Global positioning satellites, long-distance communications, airplane tracking, astronauts in space.
Roger, how does it look?
So there's an urgency in understanding what it is that the sun is doing, what's it going to do next, and how can we prepare for that and respond to it.
Worried or not worried?
Well, I would be just a little bit worried, given concern right now. We'll be watching and monitoring it very closely here in the coming days.
We've gazed at the sun since antiquity. We've worshipped it and built entire cultures around its power. We marveled when it's eclipsed during the day. And when its power lights up the night sky with dancing curtains of light, the aurora. Its power and size are awesome. It is so huge, 1 million Earths could fit inside it. Temperatures at its core soar to 27 million degrees Fahrenheit. It's been shining for over 4 billion years, and will do so for at least 4 billion more. Yet for something that has such an overwhelming influence on our lives, the sun is mysterious. How does the energy generated in its core reach us as sunlight? What processes are at work inside the sun? How do these powerful inner workings generate explosive solar storms? These are some of the mysteries scientists must understand to protect us from the sun's darker side.
The sun can really surprise us.
The sun is elusive,
Crazy,
Complicated.
crazy,
Incredibly dynamic.
crazy.
With explosive potential.
The key to that explosive behavior lies deep beneath the sun's blinding surface. Until recently, seeing inside the sun was impossible. Understanding its internal processes, a pipe dream. But an accidental discovery changes everything.
Until the 1960s, much of solar physics relied on things that were like solar dermatology. It was things that were right at the surface or just skin deep.
But as physicists study the sun in more detail, they make a surprising discovery. The surface seems to be vibrating, like ripples on a pond. Initially, they think the vibrations are the result of defective instruments.
They couldn't get rid of them. They built better instruments, the ripples were still there. They looked at it for 10 years, and they conferences, they all talked about it, and they harumphed. But what it turned out to be was just sound waves.
It is an astonishing revelation. No one expects that the sun can generate sound waves. It leads scientists to see the sun in a completely new way. Our sun vibrates like a giant pipe organ. But instead of air producing the notes, churning gases deep inside send sound waves rippling through its interior.
Because a sound wave changes as it moves through different material, we can look at the different frequencies and determine what's happening inside the sun.
Geologists are familiar with this. By studying sound waves passing through the Earth's crust, they can see the layers below our feet. A technique called seismology. Similarly, sound waves moving through the sun's interior reveal how it's made up.
I can use this organ to illustrate how sound waves work inside the sun. For example, if I hit this low note, it comes from one of these big pipes, big deep sound. And on the sun, that corresponds to a wave that goes very deep into the sun and brings back the information from deep down in the sun. If I turn to a high note, it comes from a much shorter pipe, and on the sun, that's telling us information about very close to the surface of the sun, not very deep at all into the sun.
There are 10 million different frequencies resonating in the sun. Deciphering them leads to a seismic shift in understanding its structure, creating a new science, helioseismology.
Once the helioseismology came along, we could not only see what the surface was, but we could actually tell what the physical processes were underneath. So by looking inside, we can actually see what the sun is doing.
It is a powerful tool to see beneath the sun's surface. Studying the sun's sound waves reveals a complex, multi-layered machine. Directly beneath its blazing surface is a zone of perpetual churning. Next is a layer where light takes thousands of years to cross. At the center is the sun's core. It's the smallest region, but it's over 25 times the diameter of Earth. This is the powerhouse of our star. Everything we experience on Earth, sunlight, heat, and the effects of solar storms, starts here. So what's it like here? What's the core made of?
Well, the sun's a crazy place, right? It's far too hot to be a solid. We know that. Heat it up, it's far too hot to be a liquid. And so you think, well, it's a gas, right? Well, not really. It is this gaseous soup of charged particles that we call plasma.
You're more familiar with this soup than you might think.
There are plenty of examples. Fluorescent light bulbs, flames, neon lights, perhaps fancy TVs that I can't afford, but these are all plasma. Plasma's sort of all around you.
But plasma is radically hotter at the sun's core. The closest thing on Earth is lightning. During thunderstorms, electric charges build up, creating lightning bolts that reach tens of thousands of degrees.
That's pretty hot, but it's nowhere near as hot as in the core of the sun. So if you were to travel into the core of the sun, the plasma would be 15 million degrees.
As the sun formed, hydrogen gas at its heart was crushed under the weight of the material above. Eventually, temperature and pressure rose so high, the hydrogen atoms broke apart into electrons and protons, creating